Geometric probability uses geometric models and compares area, lengths, and other measures to calculate probability. In the first example here, we have a circle that has parts that are yellow, blue, or white. The smallest part is yellow, then a little bit larger blue section, and then a larger white section. So we could make up a couple of questions. We could say if you threw a dart at this circle and you knew you were going to hit in the circle, and there was hitting anywhere on the circle was equally likely, what's the probability that you would land on blue? And you have to know the angle sizes, which we do. It's 120 degrees, and it's 120 out of a total of 360, which reduces to be 1/3. So the probability that you would land in blue would be 1 out of 3. Hitting the blue would be 1 out of 3. Obviously, I think it would be obvious that the probability that you would hit white would be, you could think of it as 180 out of 360, but you can also tell that half that circle is white. And then to hit yellow, the probability would be 60 out of 360, which in lowest terms is 1/6. And of course, all these probabilities together better add up to 1, and they do. Now, just as a way of showing this can get kind of complicated, this is a problem from your book, problem number 4 on page 149. And you have this diagram given, and you have really no numbers in here, just the fact that this square, the length and side of the square is 2r, so of course this side is also 2r. You have to know it's a square, and I think they tell you that it's a square. And that the radius of the circle is r. And the question poses, what's the probability that if you shot an arrow and you knew it was going to land inside the square target, and equally likely that it could land anywhere, what's the probability that it lands on yellow? So, I mean, you can take a guess. It looks like it's 1 out of 6 or something like that, but there is a way you can actually figure out exactly what it is, and it's a little bit complicated, but if you knew the area of the whole square and you knew the area of the yellow, you could just compare the area of yellow to the area of the entire square. Well, the entire square area is pretty easy to calculate. It's just the length times the width, or 2r times 2r, which would give us 4r to the second power. The area of the circle is not that complicated. We use the formula that the area of the circle is pi r squared, and in the directions it tells you to use 22/7 for pi. So like this is the area of the square. The area of the circle would be 22/7 times r squared. So we have the two quantities we compare. We want to know the area of the yellow part, so it's going to be half of 22/7. So the area of the yellow would not be 22/7, it would be half of 22/7. So how many sevenths would it be? Half of 22 would give us 11/7 r squared. Now, since we want to compare that to 4r squared, it's going to be really nice to write 4r squared as sevenths. So think about how many sevenths are in 4. And I hope you're thinking 28. So the area of the whole square is 28 out of 7. You can kind of cancel, you can just kind of forget these r squareds for a second, because that's the same number. R squared here is r squared in this one. So it's really like comparing 11/7 to 28/7. The area of the yellow is represented by 11/7, and the area of the whole square is represented by 28/7. And since they're both in the same unit, we can kind of get rid of the sevenths and just compare 11 to 28. So the probability of hitting yellow is 11 out of 28.